we're now going to look at conversion of transfer functions. So in converting transfer functions to a state model, there are three methods we could look at. There's a single input, single output method. There's a multi-input, multi-output method that we'll be using called Gilbert's realization. And then there's state space to transfer function, or TF to SS, or SS to TF, depending on which direction you're going. Okay, so this is what MATLAB uses. So how does a single input, single output system work? Well, here we have a transfer function, g of s, single input, single output. So I can actually write it as y over u. When you have a matrix or multi-input, multi-output system, you can't write it this way because u is a vector. You can't divide by a vector. Anyway, in general, I'll have a polynomial over a polynomial as my transfer function. We can go through and show that this has the controllable canonical form realization, and we've already seen this. And notice I have the coefficients b's and the coefficients a's. So if you remember from the difference equation, or the differential equation rather, the b's were multiplying u, the a's were multiplying the y's and derivatives of y. And so you can actually obtain this transfer function directly from the differential equation by taking the Laplace transform of the entire equation and assuming zero initial conditions. Basically, that would give all of these guys multiplying y, all of these guys multiplying u. We would factor these guys out and factor these guys out, and then just form the ratio y over u, and we get the transfer function. So that differential equation that I showed, that nth order differential equation, had this controllable canonical form, and you can see here it's the same controllable canonical form. I can take this transfer function and just directly plug in the a values and directly plug in the b values, and I'm done. Boom. So that's the single input, single output method. And again, we could also, this is the controllable canonical form. We could also do the observable canonical form. So we could do it that way. This is in continuous time. We would basically do the same type of thing in discrete time. In discrete time, we would have a transfer function, a polynomial in z over a polynomial in z, and we can again put it into controllable canonical form, and this is the form we would get. So I'll do an example of this so you can see exactly how it looks, but this is the form that we're going to be working with. So single input, single output method is pretty straightforward. In fact, you have a formula that you can use. For multi-input, multi-output system, it's a little more complicated. For now, I'm going to assume we have simple poles. Okay, simple poles means they're not repeated. In general, the poles may be complex. If P is complex, P1 is complex, R1 will be a complex matrix. So this is a matrix partial fraction expansion. So if you have a matrix, and the matrix is a matrix of single input, single output transfer functions, you perform partial fraction expansion on each of the terms in the matrix. And then the matrix partial fraction expansion takes all the partial fraction expansion denominator terms and creates a sum of all of them. And then the matrix that you get is the matrix that has coefficients of the partial fraction expansion in those particular places and zeros in the other places. Okay, so these matrices R1 through Rn may be complex, and in general they may be sparse, that is mostly zeros. Alright, so in general we're looking for a model like this. X dot is equal to ax plus bu, y is equal to cx plus du. So how do we get that from this? Notice the d is kind of a giveaway. The d is the thing that just comes through. That's the direct feed-through term, or sometimes referred to as the high-frequency gain. So we first look at the high-frequency gain. We look at this function. As s goes to infinity, notice that R1 through Rn, those are constant matrices. And so as s goes to infinity, each of these guys goes to 0. And so you can see that if you take the function g as s goes to infinity, we're left with the matrix D. So it's often referred to as the high frequency gain, s going to infinity, s being a frequency variable, going to infinity, that's high frequency. If we're given a transfer function, this is how we find the D matrix. We evaluate the function as s goes to infinity. We then do the partial fraction expansion on the rest, okay, that is on G minus D. We do the partial fraction expansion on that. I'm going to give you the realization, the Gilbert's realization. The A matrix is going to be of this form. It's going to be a diagonal matrix with the poles P1 through Pn appearing along the diagonal. And each of the poles may be repeated a number of times. So even though I say this is simple poles, what I mean by that is these guys are simple. That is, I do not get repeated values when I do this partial fraction expansion. Okay, so in this case, the A matrix is not defective. So even though it has repeated poles, it's not defective, it's diagonal. The number Ri, so that is, I'm going to have basically a block diagonal matrix where each block is of dimension Ri. So R1 is the rank of R1. Okay, so I look at each of these matrices and I look at the rank of each of those matrices. That rank tells me how many of these guys I need to string together. So that's how I form the A matrix. The A matrix is going to be a diagonal matrix. To obtain the C matrix and the B matrices, I perform an LR factorization. So we talked a little bit about LR factorizations in the last unit. Basically, I can, for any matrix, I can factor a matrix into a product of two matrices. Each of these matrices, Ci and Bi, are full rank. Okay, so remember the rank of Ri is little ri. And so in general, our transfer function matrix is of dimension P by M. And so Ci is going to be of dimension P by Ri. B is going to be of dimension Ri by M. Okay, so this is going to be like kind of a column-ish thing. This is going to be kind of a row-ish thing. And so I stack these rows together to form the overall B matrix. I stack these columns side by side, column-ish things side by side to form the C matrix. And that's the Gilbert's realization. The R's will be complex, the poles may be complex. That will give us a complex A matrix and complex B and C matrices. And so in general, we may want a real realization as opposed to a complex realization. And so we can use this instead of using diagonals like this, I would basically use the fact that this transfer function, which has complex poles at -1 plus or minus j, minus a1 plus or minus j a0, this transfer function has this state model. Okay, and so we can go through it that way instead. Right, so we can get a real realization. It takes a little bit more work to do that. State space to continuous time, state space to transfer function. How do we get the transfer function from the state space now? Well, we have x dot is equal to ax plus bu. So if I take the Laplace transform of both sides of this equation, the Laplace transform of this is this. Again, we have an initial condition. Assuming zero initial condition, this term goes away. The Laplace transform of this side becomes ax of s plus bu of s. I have now s times x of s is equal to a times x of s plus bu of s. This guy is 0. I can take this guy over to the other side, factor out x of s. I would get s times I minus a times x of s is equal to bu of s. And solving for x of s, then, I would multiply through on the left by the inverse of si minus a. And so I have an expression for x of s in terms of u of s. I can now work with the output equation, y is equal to cx plus du. So x now, so taking the Laplace transform, y of s is equal to cx of s plus du of s. X of s I've already solved for. It's c si minus a inverse b. I'm sorry. It's si minus a inverse b times u. And so here I'm going to get c times si minus a inverse b times u plus d if I factor out u out of all this. So all of this is the transfer function. I can do a similar thing with discrete time system. X of x at the next time is equal to ax at the present time plus bu at the present time. Taking the z transform of that gives me this. Okay. Again, I can take the, in this case I take the initial condition over the other side. I take this over to the other side. I solve for x of z and I get this. Notice that for zero initial condition this term goes away and I again get the same kinds of transfer function matrix as I had for continuous time. So if I have x dot is equal to ax plus bu, y is equal to cx plus du, this is my transfer function. If I have x at time t plus 1 is equal to ax of t plus bu of t, and y is equal to cx plus du, I get this transfer function. Again, we're assuming zero initial conditions. So that's how I get a transfer function from a state model. Now, remember, in general, I may have an initial condition for a system. Comes out when I have an initial condition. This is the transfer function times the input. So all of this is called the forced response. This is the response of the system when it's forced by the input u. This is referred to as the natural or homogeneous response of the system. This is the response of the system when you have no input and an initial condition. So that's the form that we get in general in the Laplace domain. So that's for a continuous time system. For a discrete time system, this is the form. We get the exact same kind of form happening with continuous and discrete. So covering continuous and discrete at the same time, we actually have a lot of the same tools that we're using, and we're going to see a lot of similarities between what happens in continuous time, what happens in discrete time. Clearly, the types of systems are different, but we can actually use a lot of the same tools. So in summary, given a transfer function matrix, there are canonical forms into which the system can be put. If we're given a block diagram, we can obtain we can combine individual blocks to form an overall state model. Given a state model, we can obtain a transfer function matrix. Stay tuned for the practice problems.